or a stick insect, or a hemoglobin molecule, by sheer luck. Well, my reason for mentioning Hoyle 747 is that I'm going to take his name in vain in the next demonstration. We're going to have a computer monkey, or rather, we're going to have two computer monkeys, one called Hoyle and one called Darwin. Both monkeys have the same task. Both have to type not the complete works of Shakespeare, but one phrase from As You Like It, more giddy in my desires than a monkey. Hoyle types entirely at random. After every line that he types, the computer checks to see if he has managed to hit the target line. If he does, the computer will stop, bells will ring, it'll be the most improbable coincidence in the history of the world, and I solemnly promise to eat my hat. I'll go further than that. I bet you everything I possess that it won't reach the phrase. Shall we say in the next 10 billion years. I won't bet you, I'll undertake to give everything I possess to the Royal Institution, and here's a legal document signed by me which undertakes to make over everything I own to the Royal Institution in the event that the monkey Hoyle reaches the target phrase. But of course, this is just to illustrate my confidence that chance on its own could never make an I or a 747. The real point of the demonstration is that the other monkey, Darwin, will get the target phrase. So what does Darwin do? The same, but with a crucial difference. The Darwin monkey begins by typing a random phrase. So far it's the same as the Hoyle monkey. But now the computer breeds from that phrase. It breeds 50 offspring, which are identical to the first phrase, but with a tiny mutation, a tiny random difference in each of the 50 cases. The computer then looks at those 50 offspring and chooses the one which most resembles the target phrase, however slightly it resembles the target phrase. So the generations go by, and after generation, it gradually becomes more and more like the target phrase. Now, when I agreed to give these lectures, I was told that I should always call members of the audience out to assist, but I was also told that it was silly to do this if all I was going to ask them to do was to come out and hit the return button on a computer. However, on this particular occasion, since so much is at stake, I thought it would be better if I did ask somebody who knows a lot about computers and is very good at pressing buttons to come out and perform this onerous task. So, would anybody like to volunteer to... Yes, right, you there. Now, what's your name? Andrew. Well, you understand what's at stake, Andrew, do you? Okay. Here's the target phrase, more giddy in my desires than a monkey. There's the box where the Hoyle monkey is going to type, and there's the box where the Darwin monkey is going to type. And unless Bryson's been messing around with the program in order to deprive me of my worldly goods, that's the way it's going to be. So, are you ready? Go. Now you see the Hoyle monkey typing away entirely at random. The Darwin monkey is down here, and I think we can begin to see something appearing in the Darwin row. More if giddy in my desires than bang, and it's got there. How long did that take? Anybody time it? Not very long, I think. Anyway, thank you very much. So I don't have to eat my hat, and my worldly goods, such as they are safe. But the point really is not that Hoyle failed to reach the target. The point is that Darwin did reach the target, and astonishingly quickly. Well, there's a lot wrong with that as a demonstration of Darwinian natural selection. For one thing, it has a distant target in mind, which natural selection does not have. But it does once again show us the key to the way out of the problem of mammoth improbability. Things like I's and 747s that couldn't possibly spring into existence in a single lucky shake of a dice can come into existence if the luck is smeared out in many tiny steps and is accumulated. And that's what this lecture's about. Smearing out the luck, accumulating it, turns out to be an immensely important process. It's the process that makes it possible for us to be here, and by us I mean all stick insects, lions, elephants, and bacteria, everything that's here. And now let's look at a physical parable for this gradualistic solution to a difficult problem. This is a mountain. It's called Mount Improbable. Sitting on the top of the mountain is equivalent to being very well designed, to being an eye that works very well, for example. Being at the bottom of the mountain is equivalent to being a distant ancestor that is not yet very well designed, that hasn't yet acquired its good fitness to the environment. Facing you now is a precipice, a cliff, which is called sheer luck. It's a sheer cliff. Jumping from the bottom of the cliff to the top corresponds to assembling a 747 by means of a hurricane, or it corresponds to getting a complete eye in a single lucky mutation. It can't be done. You can no more do that than a mountaineer could leap from the bottom of a cliff to the top. But this isn't the only route up Mount Improbable. We have to go round the other side. And you'll notice that round here is a gradual, sloping path, steadily inching its way up the mountain. And if you follow it round, you'll find that even though some bits of it are a little bit steep, you can get from the bottom to the top without ever having to jump up a step. It's a gradual, inch-by-inch path up. Anybody who didn't know about the ramp evolution, which is what that's called, would, if they saw an animal perched on the top, a beautifully designed animal, and only saw the cliff, they would assume that it had to be the result of a miracle. But in fact, the only way up Mount Improbable is the slow, gradual climb up the ramp evolution. You have to add all the little steps up together, and after a very large number of steps, you can climb very, very high indeed. But we're still talking in parables. How in practice do living things climb Mount Improbable? Well, of course, individuals don't climb it. It's lineages, groups of animals, species that climb it, and they do it in evolutionary time, they and their descendants and their descendants' descendants. They do it by going through an extremely large number of generations, and we do have the time for an extremely large number of generations because we have geological time at our disposal. This generation by generation accumulation works only if there is reproduction with true heredity to carry the message through. And I must explain what that means, because just plain reproduction without heredity won't do. It's not enough. It's possible to imagine reproduction without heredity. Fires, for example, have a form of reproduction without heredity. If you imagine that this is a savanna, a dry savanna with dry grass all over it, and a fire suddenly starts in one place, sparks fly up and are carried in the wind, and suddenly a spark lands there and a new fire starts. Both these fires are now flaming up and sparks are going off, and another fire starts up, which may be the daughter of this one. One starts up here, which may be the daughter of that one. These fires are propagating. These fires are having children. The sparks are causing this fire to be the parent of that one, and in the next one we can see that you can have both not mother and daughter but grandmother, grandchildren fires. Now, the fires may differ a bit. In this picture we've represented them by red, green and blue. Fires may indeed differ, but they get their qualities not from their parents and grandparents. A fire gets its qualities from its surroundings, from its environment. A fire gets its qualities from the direction of the wind where it happens to be, or from the chemistry of the soil, or from the dampness of the vegetation. Fires do not get their qualities from the spark that comes from their parent fire. Now we're going to do the same thing with a Bryson special. And I'm going to stand well back, I think. Where do I have to stand? Here? Right.